In this phenomena, we added a little bit of water inside a syringe, sealed it off, then pulled the plunger. This caused the water to boil. Notice this is not just a surface phenomenon. The boiling occurs throughout the liquid. As we slowly release the plunger, notice the boiling slows down and stops. As we pull more on the plunger, the boiling becomes more vigorous. Let's explain this phenomenon. We put a little bit of water into the syringe, and water has a low vapor pressure at room temperature. What that means is, because of its high intermolecular forces, namely its hydrogen bonds, it doesn't vaporize easily. The vapor molecules above the liquid in a closed system, like the syringe, when they collide, they produce what's called vapor pressure. Now, why doesn't water boil at room temperature? Well, that's because there's air particles from the atmosphere colliding above the liquid and causing pressure on the surface of the liquid. Let's call that external pressure. You can see by the diagram, the external pressure is greater than the vapor pressure of the water, at least at room temperature. Now, this water was heated to about 80 degrees Celsius, so it wasn't room temperature, but it wasn't quite at the normal boiling point either. So let's see what happened when we pulled the syringe. By greatly increasing the volume, we greatly decrease the pressure. This is known as Boyle's law. And you can see that because before I represented the air pressure with 7 black dots. Now those 7 black dots, which represent all the air particles that were in the syringe, are now colliding in a volume 2, 3, 4 times larger in our case. So this diagram is not drawn to scale. So if the volume increases 3 times, the pressure is going to decrease by that same factor. So we significantly decreased the external pressure, so much so that it equaled the vapor pressure of the water. And by definition, when the vapor pressure of a liquid is equal to the pressure above that liquid, the external pressure, then that liquid boils. And you saw in our phenomena that boiling occurred throughout the liquid, not just the surface. Those water molecules had enough kinetic energy to overcome the intermolecular forces and the external pressure of the air above it. So boiling happens when the vapor pressure is equal to the external pressure. And in this phenomenon, we didn't change the vapor pressure of water, but we decreased the external pressure, and therefore we caused the water to boil. Let's see how this might look on a phase diagram. A phase diagram relates the pressure of a substance to its temperature, and it's like a map on how to navigate the phases. Water's phase diagram looks something like this. There's a triple point, there's a solid-liquid equilibrium, there's the critical point, and we have our phases: solid, liquid, and vapor. In our room, we're at about 1 standard atmosphere. So this here is called the normal boiling point. That's 100 degrees Celsius. And over here is the normal melting point, or freezing point, 0 degrees Celsius. The water in our syringe was somewhere around there. All points on this equilibrium line in red represent all the boiling points of water. There's a couple ways you can get to that equilibrium line. The most familiar way for most people is by increasing the temperature. By increasing the temperature from where we're at, we can hit that equilibrium called the boiling point. But that's not how we cause our water to boil. The other way is to decrease the pressure. And that's what we did on a syringe. We started there. I'm going to zoom in a little bit. And we went down to hit that equilibrium line called the boiling point. So hopefully you can see through the phase diagram, as well as conceptually, how we were able to make water boil by pulling in our syringes. I have some warm water in a sealed flask, and I'm going to pour ice water over it. In this phenomenon, we're going to boil water by decreasing the temperature. Get a good angle. Let's explain this phenomenon. We added some water to a flask and we sealed it. This is a closed system. I heated the water in the flask a little less than the normal boiling point. Let's say around 80 degrees Celsius. Now at 80 degrees Celsius, the particles that make up the liquid water have more kinetic energy than they would at room temperature, which is around 25 degrees Celsius. Let's say these 4 blue vapor molecules in blue represent the vapor pressure of water at 80 degrees Celsius. Now water is not going to boil at 80 degrees Celsius because it's still less than the atmospheric pressure pushing down on it. So I'll draw 5 black dots to represent the external pressure above the liquid. So the air particles in the flask above the liquid water, let's say, is 1 atmosphere. And since we know the water wasn't boiling initially, let's say water's vapor pressure is less than 1 atmospheric pressure. In order to boil a liquid, the vapor pressure of the liquid must equal the external pressure above the liquid. There's a couple ways we can do that. We can continue to heat the water in the flask, or in our case, we decrease the atmospheric pressure. We lower the temperature, so we poured ice water over this flask. So we lower the temperature by pouring ice water over the flask. Now, because of water's high specific heat, the liquid portion doesn't change as rapidly as the air particles in the flask. So by decreasing the temperature of the air in the flask, we decrease the external pressure. By the way, this is known as Gay-Lussac's law. So by lowering the pressure to match the vapor pressure of the water, we cause the water in the flask to boil by lowering the temperature. But by lowering the temperature, we really decrease the pressure significantly more of the air above it. In this phenomenon, we're going to show you ice water boiling by taking you close to the triple point of water. We have a beaker of water. Add a few drops of green food coloring, just so we can see better. This is a vacuum pump. I have it covered with this jar, and we're going to pump the air out of this, try to create a low pressure environment in that jar. Let's see what happens. Notice we're starting to get bubbles forming. So as we remove more air, the air pressure inside the jar decreases, allowing the vapor pressure to match the external pressure causing the liquid to boil. Boiling ice water. Finally, how do we get ice water to boil? So I placed a beaker of ice water out in the open. And the reason why ice water doesn't boil when left in a room is because the atmospheric pressure, or the external pressure, is greater than the vapor pressure of the water. And where we are, which is around standard atmospheric pressure, that's about 1 atm, or about 101 kilopascals. Now what happened when we covered this up with the jar, sealed it, and started pumping the air out? And that's going to decrease the collisions of those air particles above the liquid of the water. That's going to greatly reduce the atmospheric pressure, or the external pressure, above the liquid. And we did that until it matched the vapor pressure of the liquid water. And once it did that, then it started to boil. Again, we can map this out using a phase diagram. Water's phase diagram looks something like this. There's a triple point, there's a negative slope for the equilibrium line between solid and liquid, and there's the critical point. Solid, liquid, and vapor. This blue line represents the air pressure in our room, which is about 1 atmosphere. This red line represents the equilibrium between liquid and gas. Every point on this red line represents a boiling point at a specific pressure and temperature. This point here represents the normal boiling point of water, which means the boiling point at 1 atmosphere, and that's 100 degrees Celsius. I'm sorry, this x-axis represents temperature, and this y-axis represents pressure. This point here, on that blue line, where the solid phase meets the liquid phase, that's known as the normal melting point, or normal freezing point. And at 1 atmosphere, water freezes at 0 degrees Celsius. All right, I added ice to this water to try to get it close to 0 degrees, because that's about above the triple point. So what I wanted to show you was the triple point of water, where we have freezing and boiling happen at the same time. Now, I didn't have the equipment to manipulate both pressure and temperature simultaneously, so I had to control one at a time, which is why I added ice to bring the temperature above the triple point, which is that point right there where the 3 phases meet. And then I used my vacuum pump to lower the pressure to get near that triple point. So we didn't quite see the triple point of water, but we got close.